All right, thank you. I thank you for the organizer to giving me opportunity to deliver this presentation. Well, my presentation is on the B-bar virtual element formulation for nearly incompressible and compressive solids. And this work is done with the collaboration 2021. Okay. So basically, this is the outline of today's presentation, where I'll start with a very brief motivation on the polygonal and polyhedral elements. And then I'm going to talk about the virtual element formulation very briefly. So because well, here will be, everybody will be very expert on the VEM. And then I'm going to talk about how did I extend the VEM formulation for B-bar VEM. And then next, where I'm going to demonstrate the eigenvalue analysis for the polygonal and polyhedral elements. And then going to show computational examples in the engineering perspectives. Okay, I'm going to show engineering numerical examples. And then finally, I will summarize today's presentation. So, well, as you guys know, well, we have the great flexibility on the discretization if we are able to handle, let's say, polygonal and polyhedral element shape. So, well, we could utilize it for CFT simulation, and also based on, let's say, CAD geometry, where we could easily describe relatively complex geometry using many edges and many faces on the elements. So that is also very great potential on the polygonal elements. And furthermore, well, also polygonal elements demonstrate great performance on the high, very large deformation as well. So then today, what I'm going to talk about is basically for the nearly incompressible and compressible materials. So in classically, well, VEM, well, it can handle both highly non-convex elements, even both in 2D and 3-dimensional case. And furthermore, well, we can also handle even non-simply connected elements, let's say elements inside with a hole in it. So then, well, I'm going to solve the elasticity problem, where this will be our, let's say, simple governing equation, and virtual displacement space is defined in each element first. And then this virtual element space is first for the polygonal space in 2D. In the polygon, where first we define the preliminary space, where Laplacian of our virtual space is within the linear polynomial space, and along the edge, well, it varies linearly. And then we also define the projection operator, let's say pi nabla, and pi nabla of our virtual displacement field is within the P1 linear polynomial space. And then this projection operator can be uniquely defined using the vertex information as shown in this formula. Then using this projection operator and preliminary virtual space, we define local virtual element space as follows. So this is the defined space in 2D polygon. And then we could extend it to the 3-dimensional space as well. Right, as we did in the 2D case, our space, let's say Laplacian of the displacement is within the linear space, and also on the face is derived from the virtual space on the face. So then we could also uniquely determine the pi nabla projection operator in the 3-dimensional space as well. Then finally, as we did in 2D case, we can also define the local virtual element space as in this formula as well. So this is very brief description on the, let's say, virtual element method. So then, well, I'm going to talk about the B-bar VEM. Okay. So when the Poisson's ratio is close to, let's say, 0.5, well, we would have a locking behavior where we want to avoid the locking behavior. So the most popular method was B-bar method. So motivated from the B-bar FEM, well, as shown in this reference, where we split our material stiffness into two parts, dilatational part and deviatoric components. Well, how do we split it? Well, we could use the spectral decomposition. Okay, our, let's say, material stiffness can be decomposed into eigenvalues and eigenvectors. Well, the eigenvectors will be the basis vectors. And depending on the size of our material stiffness matrix, well, we could decompose our, let's say, stiffness matrices. And for the dilatational deformation, is associated with these eigenvectors, right? So first one is, this vector is for 3D, and this one is for 2D case. And then corresponding eigenvalue will be related to the Burke modulus, 3K for 3D. So this is for 2D case. So then using these eigenvalues and eigenvectors, well, we could construct the material stiffness for the dilatation part. And then the difference from the original, let's say, material stiffness and then the dilatation part will be the material stiffness for the deviatoric part. And then calculated, let's say, deviatoric stiffness compound is written as follows. This is for the 3D, and this is for the 2D case. So then the calculation procedure is very straightforward and simple. And furthermore, as you guys may see in this title, well, we could further extend it to anisotropic elastic material behavior as well. But here, well, I'm just considered in isotropic material. So then in the VEM formulation, well, element stiffness matrix consists of two parts, right? Consistency terms and stability terms. So in the consistency term of the element stiffness matrix, where this will decompose also into two parts, right? Deviatoric part and dilatational part. And simply, well, deviatoric part will be, let's say, B transpose C, dev BC, where this is the deviatoric part of the consistency matrix, and BC transpose C dilatation and BC, where this will be dilatation part of the consistency matrix. So B is, let's say, these are B matrix, as you guys know, where it relates displacement versus strain relations. So then this will be the derivatives of our projection of our shape functions, right? So we can determine, let's say, this B matrix. So then finally, well, our consistency matrix is, let's say, as we calculating, let's say, it consists of the deviatoric part and dilatation part. Adding these two together will be, let's say, BC transpose C BC. So this is our consistency term of our element stiffness matrix. So in the next, when we are stabilizing our element stiffness matrix, well, here's the difference. Well, we are stabilizing our element stiffness matrix based on the diagonal entries of the deviatoric part of the consistency matrix. Okay, so we are only considering, okay, deviatoric part of the consistency matrix, and then while we put the lower limit as a, let's say, half of shear modulus to have a proper scaling. So then while we use the diagonal recipes to reconstruct the stability terms of the stabilization terms of the element stiffness matrix. So then using this formulation, well, then we did eigenvalue analysis for both 2D and 3D. So then we generated, let's say, about 50 elements in the 1 by 1 or 1 by 1 by 1 domain. Elastic modulus and Poisson's ratios are arbitrarily selected, let's say 100, and for the 0.25, and the other one is, let's say, 0.4995, which is very close to 0.5. Okay. So then, well, first, let us take a look at, let's say, simple one. Let's say when Poisson's ratio is 0.25, right? So this is the results for the 2D, and right-hand side is for the 3D. So then when we compared, let's say, 3 computational approaches, let's say finite element approach, where we are using watch press element shape functions for the calculation of element stiffness matrix. And then second approach will be standard VEM, where we use the diagonal entries of the stiffness matrix. Okay, so that's adding both dilatation part and the deviatoric part. And B-bar VEM, where we are just using deviatoric part only for the stabilization. So that's the only differences. So these are, let's say, comparison among the 3 approaches. So while they are in the similar orders of magnitudes, and some eigenvalues are identical among each other, especially for the constant strain energy mode. For higher energy mode, well, definitely where we would expect to have some differences. So, well, as you guys can see, some eigenvalues we would see some differences. So while these are eigenvalue analysis for the, let's say, compressive material when Poisson's ratio is 0.25. For the case of nearly incompressible material case, so left-hand side is again for 2D and right-hand side is for 3D. So the values are differences are several orders of magnitude differences, right? It varies from 10 to the power of 6 to the about 10, right? We have a wide range of differences in the eigenvalues for both 2D and 3D, right? And also the largest value, well, this largest value related to the dilatational mode, okay? Dilatational mode. And also around this part in the, let's say, smaller eigenvalues are also related to the other constant strain energy modes, okay? In between values are describing, let's say, higher order modes, okay? So then FEM case, well, it's widely distributed. So eigenvalues are populated in the wide range. And for the standard VEM, well, we have the relatively large eigenvalues expected. Let's say it's a 10 to the power 5th and 4th in 2D and 3D case. However, in B-bar VEM, except the dilatation mode, all other eigenvalues are placed, let's say, in the relatively smaller values, right? So this is the main differences. So to confirm, let's say, energy mode differences, well, what it did was, well, we separated, let's say, eigen analysis into 2 parts, let's say consistency term and the stability terms. Okay, the consistency term is related to the constant, let's say, strain energy mode, and then therefore, well, we have the 6 eigenvalues. So among the 3 approaches where their eigenvalues are identical, okay, as we could expect. For the stability terms, well, we would see the clear differences. For standard FEM, well, we have, well, as I described before, we have the very wide distribution on the eigenvalues. For the standard VEM, well, we have relatively higher, let's say, eigenvalues. For B-bar VEM, well, we could reduce the higher modes of eigenvalues. So then, therefore, well, we could eliminate or reduce locking behavior for nearly incompressible materials. Okay, so then now let us move to the, let's say, actual engineering let's say, applications. So when we solve the boundary value problems for both 2D and 3-dimensional elastic solid. So well, first example was a cantilever where we have a rectangular domain and boundary conditions are described in this figure. And let's say forces applied with the quadratic function shown here. It has the following analytical solutions. So then while we use the 3 different types of meshes, so CVT and Pegasus and VEM, letter type elements. Okay. And these are, let's say, convergence research. Well, we studied convergence, rate of convergence, while, let's say, decreasing the element size while we achieve the linear rate of convergence of 2. Well, it's theoretical values. And regardless of element types, well, we achieve the optimal rate of convergence for both compressible and nearly incompressible materials for both cases. And also the accuracies are also very similar to each other. The accuracy difference is more depends on the mesh type, mesh quality, right? If you compare the scaling on the error, okay? And then next, then this is the second example where we have a, let's say, 1x1 square domain and all other, let's say, edges are constrained, but on the upper surface where we apply the uniform vertical displacement within the 1/3 of the domain, okay? So then when we are, let's say, solving this kind of problem using, let's say, polygonal elements, well, these boundary points does not necessarily, may not correspond to the nodal location, right? So then there will be, let's say, when I generating meshes where I employ 2 approaches. Let's say first approach is where I select the closest node to this boundary position and simply relocated the node, relocated the nodal location. So this is mesh type 1. And alternatively, well, I just simply added a new node on the edges. So I'll split the edges, okay? So using these approaches where I look at the convergence of the solution, where it's showing in these 2 plots, while increasing the number of elements, where we would clearly see the convergence of our solution for both mesh type as well. Okay. And this is also, let's say, comparison of the pressure field. So if we use the, let's say, B-bar VEM, where we would get very smooth and stable pressure field, but if we have if we use standard VEM where we have some oscillation, it is not stable. And this is the third example, where I also solved the Cook's beam example, and material properties are summarized as follows. Well, I use the Poisson's ratio of 0.4995. It's very close to 0.5. Here, where I use the 4 types of the meshes. So polygonal centroidal Voronoi tessellation, CVT, and random Voronoi tessellation, let's say RVT, Pegasus, and bird types. Okay, well, we have the 4 mesh types. And then when I investigated the convergence of our numerical solution under the mesh refinement. So while increasing the number of elements along the horizontal axis, where vertical displacement where shows the convergence to the reference solution for both the compressible and nearly incompressible materials. So this dashed line indicates, let's say, reference solution, where this is obtained from the commercial software Abacus with the, let's say, 1 million bilinear quadrilateral elements with the constant pressure condition. Okay. So regardless, okay, again, mesh types, element types, well, it shows the convergence to the reference solution. Okay. And then, well, this also shows the pressure field. So even though where we use the highly non-convex elements, so pressure field is very smooth. Okay, so I think this is main advantage on the virtual element method. And also, where I also compare the convergence to other computational approaches, let's say B-bar VEM and B-bar FEM, standard VEM and standard FEM. Okay, so using, let's say, polygonal elements, let's say CVT meshes. So where I investigate the convergence among these 4 different numerical methods. So as we could expect, VEM shows the most accurate result, okay, for the nearly incompressible materials. The next one, second best was B-bar FEM. Okay, second best was the B-bar FEM. And standard VEM and standard VEM was less accurate than the other 2 approaches, as we could expect. So well, this is for the case of the nearly incompressible case, when Poisson's ratio is 0.49995. Okay. So then, well, I also checked the effect of the Poisson's ratio. So when with the number of elements is, let's say, 400, and we select the meshes and then change the Poisson's ratio. Okay, here. So then when Poisson's ratio is smaller than 0.4, okay, then the vertical displacement values are quite similar, right? Their values are very similar among each other, but it approaches to, let's say, 0.5, right? It approaches to the nearly incompressible material, well, you'd see distinct differences. When it's a 0.49, well, we have some small differences. Well, if I select 0.49995, right, well, you'd see the accuracy differences in this figure, okay? Well, this is the last example. And I solved the 3-dimensional problems where in the box domain where constant compressive displacement is applied on the half of top surface as described in this figure, and also all the other remaining faces are constrained. Okay, so this is named as 3D constrained block examples. Okay, and then material properties are also specified as here. And then while increasing the number of elements while we investigate the convergence studies. And also when I generating these meshes, well, matching, let's say aligning the edges, a little bit challenging for me. So then when I generating the mesh, first, well, I generated the polyhedral elements within the box domain. Well, that's a simple to generate. And then, well, I just simply split the face to match with the displacement boundary. Okay, so this is also main advantage in the VEM. So then, well, this shows the nice vertical displacement field. Okay, so continuous. Okay, and these are convergence studies. So well, I basically average the vertical displacement along this left upper edges. So I average this vertical displacement along this line, and then compared with the reference solution obtained from the abacus. So I used 2 million elements with the constant pressure elements. So well, using B-bar VEM, well, it shows the solution is very close to the reference solution. But if you use the standard VEM, well, it's far away from the reference solution. And also, well, this is the last one. Well, I also showing the pressure field. So if you use the B-bar VEM, well, we have the very smooth and nice pressure field. But if you use standard VEM, well, we have some oscillation and strange pressure field is expected. So this is the summary of today's presentation. Well, virtual element method with B-bar method can effectively simulate both compressible and nearly incompressible solid. Okay. So in B-bar VEM, well, deviatoric part of the consistency matrix is used for the stabilization. Okay. So this consistency part of the deviatory stiffness matrix is evaluated using deviatoric part of the material stiffness, where we can get this from the spectral decomposition technique. The most eigenvalues of B-bar VEM are several orders of magnitude lower than the standard VEM and FEM, and then therefore, well, we can reduce the locking behavior, right? And computational example in both 2D and 3D are solved, and well, it shows very nice pressure field and very relatively accurate results are observed. And also in polygonal and polyhedron meshes, and edges and faces are split to match with the boundary condition in the mesh generation process. And the last, where optimal rate of convergence and stable pressure field are achieved regardless element shape, let's say both convex and non-convex. Well, I thank you for your attention.